All right. So welcome everyone. So today we'll have Habib from University of Montreal to tell us about the Lagrangian spectral estimators and the fragmentations in dimension 4.
Yeah, thank you very much for the introduction and thanks for inviting me. Yeah, as was said, like I'll be talking about Lagrangian spectral estimators and this fragmentation phenomena that was already known only in dimension 2. And now we'll see how one can do fragmentation in dimension 4 using pseudo-holomorphic techniques. I will be talking about fragmentation, its history and applications in the beginning. And then we'll see what is the input from theory of pseudo-holomorphic curves in dimension 4, which kind of helps us to prove some extension lemma, which is the core of the fragmentation lemma. And then we'll see what the extension lemma is. And then as a consequence, we'll prove the fragmentation lemma. And then if there is time, I have a few slides on Lagrangian spectral estimators. I will introduce them because they're kind of the main object of the talk. Even though, like, I mean, basically the novelty of the paper is about fragmentation and doing, fragmentation dimension 4, but they're kind of mainly used, and the motivation for this fragmentation result was to prove C0 continuity of these spectral estimators. So it would be nice to kind of introduce them, how they're constructed. And then at the end, we'll see some, we'll see like this C0 continuity and some other applications. Okay. Some very quick basics of symplectic geometry first. So M omega is called symplectic if omega is like a closed non-degenerate 2 form. And then if you take a time-dependent, do you see my cursor when I move this? Okay. If you take a smooth time-dependent function, you can associate to it an isotropy, right, phi t, through these equations, these two equations. So basically, you define xt as the dual of differential of h, omega dual, and then you integrate it, you get an isotropy, and this isotropy you can prove that it's preserving the symplectic form. And the time one map is called the Hamiltonian diffeomorphism. And the set of Hamiltonian diffeomorphism is denoted by Ham. So one notion that I will need in the course of the talk is the displacement energy of a subset of M, a kind of pre-compact subset of M. And it is defined as the infimum of the Hofer energy of H that you need kind of to displace your open subset. So given an open subset U, I will look at all the smooth functions whose time one map is displacing my open subset. I look at the Hofer norm, and then I infimize over all these guys. And the Hofer norm is defined simply using this formula. So it's like integral of the max of ht over minus mean of ht over m, and the integral is over time. So a small remark that we'll need later on is that if I take a disk in a two-dimensional sphere, then the displacement energy is equal to its, like let's say a connected disk. The displacement energy is equal to its area. Okay. In other words, its capacity. Okay. Is there any question on definitions? Okay. So what do we mean by fragmentation? So in general, there's this question that seems to be very hard to kind of solve in higher dimensions, and it's basically solved in dimension 2. Is the following. So if you have a compact symplectic manifold and you're given a small epsilon, does there exist a small delta and a number n, big N, such that any Hamiltonian diffeomorphism of M that is C0 small, it's very close to identity in the C0 topology, can be written as a composition of a bunch of simpler Hamiltonian diffeomorphisms, phi 1 to phi n. And by simpler, what do we mean by simple Hamiltonian diffeomorphism? Well, normally people care about different things, and different definitions of simple has different applications. So the first one is one would like phi i's to be supported in balls of a given covering. So let's say, so the question would be, I'm given a covering of my manifold, and I'm given some epsilon. Can I find, can I find a small neighborhood of the identity such that any map there can be decomposed into things, into Hamiltonian diffeomorphisms supported in one of these balls in the covering. And if you prove such a fragmentation, such a fragmentation was kind of one of the key points in the proof of simplicity of the group of Ham, right? So Agustin Boniaga, he proved such a fragmentation. And by the way, I should note that this n actually doesn't matter. So here in this application, so this n works for any phi in this for any phi with C0 is small enough norm. So that's kind of important for the other applications, but for the first one, n is okay. You can just ignore it. You don't need like a universal n for all C0 small Hamiltonians. Okay. And the second one would be one would like the support of phi i's to be in balls of a small diameter. So diameter is smaller than epsilon. And such a fragmentation result would have applications. For example, Leroux N of Polterovich-P. They kind of proved such a fragmentation, and the application was they were able to prove some continuity of quasimorphisms on surfaces. These quasimorphisms are some functionals defined on the group of Ham. And once they're kind of continuous, they get extended to the C0 closure of Ham, and they can kind of talk about C0 symplectic geometry of surfaces. And this guy Albert Fatih is in red because basically, I think he did not have a control on this n. He was able to kind of do fragmentation and make these phi i's to be supported in balls of a small diameter, but the number of them could actually increase as you get closer to identity. But having this universal n is very important for this application. So you must have like one universal n that is working for for every Hamiltonian C0 close to identity. Okay. The next type of fragmentation that one would like to do is that these phi i's being supported in balls, it doesn't matter the size of the ball, or it's just being supported in a symplectic ball. And then what is important is that when phi gets closer to identity, these phi i's also get close to identity in C0 topology. And such a fragmentation would have interesting application. For instance, Seyfedini proved continuity of spectral norm on surfaces using such a fragmentation. Well, and this proof of this continuity is not, specialized to dimension 2. Basically, if you prove, so his proof goes through as soon as you have such a fragmentation for any symplectic manifold, right? As soon as you can prove such a fragmentation, you prove C0 continuity of the spectral norm. And C0 continuity is known for many cases, like aspherical, negative monotone. Recently, my supervisor Polterovich-Shelukhin with his collaborator Wilkins, they proved for Calabio, and And like, well, I mean, so in a work in progress, we're kind of very close to prove it for non-monotone productive spheres, but I'll mention that later. Okay. But also not known for many cases. Okay. So the other type of fragmentation that one would be interested in is like these phi i's being supported in domains of small displacement energy. So displacement energy is smaller than epsilon. And such a fragmentation was proved in well, it was proved in in here, and of Polterovich-P and Leroux, and Polterovich-Shelukhin, they used it to prove C0 continuity of their estimators in dimension 2. But so what we did here was to kind of prove this continuity in dimension 4. One other interesting application of such a fragmentation was like the proof of basically reproving the simplicity conjecture. Simplicity conjecture states that take the group of orientation preserving and area preserving homeomorphism of the two sphere. The conjecture is that this group is not simple, so it has like a proper normal subgroup. And Polterovich-Shelukhin, they were able to prove the simplicity conjecture for S2 using fragmentation in dimension 2, and proving that their estimators are C0 continuous. Okay. Any question about this history and applications? By the way, I have 1 hour, right? Okay. Thanks.
So just to be clear, like we should think of fragmentations as precisely this phi such that it can be written as a composition of n of them, or something with some condition.
Exactly, yes. So whenever I say whenever I say the word fragmentation, I mean like writing Hamiltonian diffeomorphism as a decomposition of many other ones, but those other ones, in this list, I said that one would want them to kind of satisfy some properties, and depending on the properties they have, you have different applications. Yeah, exactly. So
I have a question. So it is essential to have this Hamiltonian to be time t dependent, S1 dependent, or you can make it just purely autonomous.
these phi i's.
Yes, this phi
Yeah,
i's.
that's a good question, actually. There's like there's this norm that is kind of defined by like what is the kind of smallest n that you can have so that these phi i's are autonomous. And then like the work's done and this subject, but here we don't require them to be autonomous. So
Thank you.
here they could be just time dependent, but in this talk, I guess we'll be just working with autonomous Hamiltonians. Okay. So as I said, so we proved fragmentation dimension 4 for the first time using pseudo-holomorphic theory, and the input from holomorphic theory is the following theorem, which most of you probably know. So if you have a compact 4-dimensional symplectic manifold X, and let's assume that it does not have any embedded to a sphere with self-intersection -1. It has 2 homology classes A and B that are kind of orthogonal, meaning that it's like the intersection is 1, intersection of A and B, and self-intersection of A and B is 0. And let's also assume that A and B are represented by symplectically embedded two spheres. And now, if I'm given a symplectic embedding of you know, this domain, which is kind of drawn in this figure by in this kind of dashed area, the blue dashed area. So if I'm given like a symplectic embedding of this part into X, and where the symplectic form on this S2 times S2 is, you know, is this split symplectic form where the factors have area A and B, and A and B are the areas of these classes capital A and capital B. And let's also assume that this embedding that is given like push forwards the class of the horizontal sphere to A and the class of the vertical sphere to B. Right? Then the theorem says that you can actually extend this to a symplectomorphism. To a symplectomorphism of S2 times S2 and X. So any question about this part? Because like this is the only place that I talk about holomorphic theory. If I have time at the end of the talk, I'll say a few words kind of how one can refine this theorem to kind of extend my result, which is on disk times disk, to a sphere times a sphere. But this is the input from holomorphic theory so far. Okay. And the extension, I mean, the extension it happens on a smaller kind of area in this red part. That is not so important. Okay. So what is the extension lemma that we prove is the following. So take X, the product of two spheres, and then take this subdomain, which we think of it as you know, the upper hemisphere of the left sphere times the upper hemisphere of the right one. It's like a polydisk sitting inside this product of spheres. And suppose that phi is a Hamiltonian diffeomorphism, compact is supported. This notation means compact is supported inside M. And let's assume that it's C0 is small enough. Then there is a Hamiltonian diffeomorphism psi supported in disk times D3. So in this right, on the right hand side, you see a very thin strip that is D1, and you see this bigger one which contains the bold strip that is D2, and there is even a bigger one that is D3, right? So you have like three nested sequence of strips. The statement is that there is a Hamiltonian diffeomorphism that is supported in this bigger strip, but kind of restricts to the given Hamiltonian phi on the smaller one. So basically extends phi on this very thin strip. And it's kind of important that we are taking a strip in this statement, a strip that is kind of intersecting the boundary of the disk where phi is identity. We'll see in this sketch of the proof why that is important. Any question about the statement of the extension lemma? Okay. So the sketch of the proof, like the proof is simple given the holomorphic theory, the input from holomorphic theory that we just said. So what you would do? So these two gray disks, both of them are the right hand are the disk on the right hand side and the picture above. So let's look at this left hand side, this disk. So I will take my phi with Hamiltonian diffeomorphism that is C0 is small. I will restrict it to this gray area, to this part. And then I extend this restriction by identity in this upper part, right? So, and then I also extended this phi itself is identity in the lower hemisphere of the sphere and the right hand side. So basically the map that I get is phi here, identity above here, and identity in the lower hemisphere that you cannot see in this picture. So this is like the top view of the second sphere. So and then I will use this holomorphic this statement here to extend it to a symplectomorphism of the sphere times the sphere. And note that I did not actually, so this was supposed to be a disk, right? It's not just any subset. Sorry about that. This is kind of a mistake. So the word here instead of subset, it should be disk, and being a disk is very important in the proof of this theorem. So so we kind of the fact that kind of near the boundary your identity, you were able to kind of extend this restriction of phi by identity to this area, and if you add the lower hemisphere to this gray part, it will become a disk, and then you can use this theorem on the previous page. Otherwise, if you did not have identity near the boundary, you would not be able to connect like the upper part and the lower part, and that's going to be like a subset of the sphere with a non-trivial homology, non-trivial topology, and it's not a disk, and then you cannot use the theorem. And the refinement that I was talking about is actually this, like extending this theorem in the previous page to subsets that are not disks. So, and then okay, you get some psi 1, and then you do the same in the other direction, you get some psi 2, and then the psi that we were looking for, which is supposed to extend the phi on the smallest strip and be supported in the bigger strip, is just composition of psi 1, psi 2, and phi inverse. Okay, it's easy to check that this has the property. So let's look at like this on the small strip. On the small strip, psi 1 is equal to phi, the way we constructed. Psi 2 is also equal to phi. And then composing with phi inverse, you get phi. So you have two phi's composed with phi inverse, you get phi. And then, for example, like in this area, in the lower disk, psi 1 is phi, psi 2 is identity, and then you get phi identity, phi inverse. You get identity, and so on. Okay. Any question about the proof? Okay. And then fragmentation is an easy consequence of that. What you would do is you take your polydisk where your Hamiltonian phi is supported, compact is supported, and then you kind of divide the second disk into this many strips, which are kind of very small. And then you take like, you kind of take a 5, I should not have used this number 5. Okay, 5. And what does this 5 do? 5 do? It kind of extends the map phi on this small strips like this. This is small one, and then this one, and the other one. And it's actually supported in these gray areas. And then, of course, if I just compose phi with phi 5 inverse, it will like immediately and automatically decompose into phi 1, phi 2, phi 3, and phi 4, each of which is supported in these white strips. And then I immediately get my fragmentation. And the statement is the same. Like you have a polydisk. For any epsilon, there exists a delta such that if your phi is C0 is small enough, smaller than delta, then you can find these phi i's, which are constructed as I explained in the picture, such that phi is the composition of phi i's, and each of these phi i's are supported in in these white strips, or this or this union of these gray strips. And these gray strips, I can just choose them as small as I want. So the area of those things are very small. In particular, they have a small displacement energy. And if I increase the number of these gray strips, the area of the white strips also becomes very small. I kind of distribute them equally, and the area of the white strips will become very small. So they also satisfy this property. In particular, they have a small displacement energy by the remark that I said. So if you have like a disk on a two sphere, displacement energy is equal to its area. That's the fragmentation lemma. Is there any question about this? Okay. And okay, just one thing, that what is this delta? Like how small the phi should be, so that I can do my my kind of many extension lemmas on each of these in gray strips. Well, the only thing actually you need is that your phi kind of the image of these small strips that are kind of bounded by these two bold lines. The only thing that you need is that these small strips, the image of these guys under phi is contained inside the bigger gray strip. And that's the only thing you need kind of for the whole thing to work. So if you're just C0 is small enough, depending on the size of these strips, so that each small strip is contained inside the bigger one under phi, then you're fine. So that is how much C0 is small you need to be. Yeah. Okay. I will remind you the Hofer norm again. We'll have like a statement about like Hofer geometry, which will be very useful in the proof of continuity of spectral estimators. So the Hofer norm again for a smooth Hamiltonian is defined by the integral of max minus min. And if you're given a Hamiltonian diffeomorphism, you define the Hofer norm of phi as the infimum of the Hofer norm of H, such that phi is the time one map of the isotopy generated by H. Okay. Here we have like a theorem, which will be useful later. So let X be the product of spheres with area A and B, and then let M be the polydisk inside X. Again, think of these polydisks as the product of two upper hemispheres. And let B be a proper disk inside the second sphere. So in this picture, you can see B is somewhere here. And the statement is, for any epsilon, there exists a delta such that if the Hamiltonian diffeomorphism is C0 small enough, then there exists a psi there exists a psi that is supported inside disk times B with that is kind of epsilon far from phi in Hofer metric. So the Hofer distance of psi from phi is at most epsilon. And this psi being supported in such a domain is going to be very like crucial and important in the proof of C0 continuity. And the proof of this is quite simple. What you do is you take your phi and you fragment it into phi i's, and these phi i's, as we saw on the previous slide, they were supported in these thin strips with a small displacement energy. And then what I can do is just take, for any of these strips, take an Fi, a Hamiltonian diffeomorphism that kind of maps this strip into B, right? Well, I can kind of increase the number of strips so that their area is very small, and then you can actually fit them into B one by one. And then the only thing you need to do is kind of just take the fragments of your fragmentation, the phi i's, and conjugate them by these fi's. And note that this fi's could have very small, like I could take this disk, which is very like far away from B, but it doesn't matter. I can move this strip from, I can move it to B by a very small displacement energy, like by a very small Hofer norm. Like Fi could have like a very small Hofer norm. Like the Hofer norm of Fi could be equal to area of these disks, of these strips. Yes. So now if I kind of look at this guy, psi composed with phi inverse, just by triangular inequality, you know, I can just bound this Hofer norm by the Hofer norm of Fi's, which are very small, and then you get the result. It's just some conjugation argument. So what is important is that for any C0 of small phi, I can find a psi that is close to phi in Hofer geometry, but it's supported in such a domain for some given small ball here. Right. Any question about statement or the proof? Okay. Yes. So let's see what are the spectral estimators defined by Polterovich and Shelukhin. So take this projective sphere. One of them has area 1 and one of them has area A. A is normally supposed to be a very small number, and it's kind of supposed to be rational. You know, rationality assumption in symplectic geometry is kind of well known as you can guess where it comes from. Then you know you want to have rationality constant, and it's always very useful and helpful. Makes things makes your life easier. And they define this function also CKB. I'll tell you what are K and B. On the oops, there's a typo here. This should be here. On the space of smooth functions, time-dependent smooth functions, and they have like a bunch of properties. So I kind of just write down their names here, but I will explain a few of them in the next page. But what are these K and B? So you take this big sphere. So this is not a polydisk anymore. So sorry about this. Like I always like I'm gonna have like many pictures with two circles. Sometimes they are meant to be spheres. Sometimes they're meant to be disks. I will try to kind of mention what is it exactly. So in this case, it's actually two spheres. So you have like a big sphere times a small sphere. And K is the number of these circles, horizontal circles, and B is basically the area of this part, like this last part. So they're supposed to have like equal area in the middle. So here you have some area, here you have the same area, same area, same area, and then like just in below and above, you have area B. And the whole sphere has area 1, so area of each of these strips is like 1 minus 2b divided by k. Okay, or k minus 1. I'm not sure. K, I guess. And so what is this other line on the right? So we take the equator, and so the way these guys are constructed, they're kind of a spectral invariance of this Lagrangian link. So what is the Lagrangian link? You take this circles, this collection of circles, and you multiply them by the equator. Those are going to be Lagrangian submanifolds. And you have this Lagrangian link, and you kind of associate in some kind of a spectral invariant to this Lagrangian link, and then you define your CKB. So let me see how much time I have. Yeah, I can probably say a few words about how they are constructed. Okay, I hope I won't go over time. So, okay. First, let me tell you like some of the properties of these spectral estimators. Well, these are the only properties that we're going to use in the proof of C0 continuity. Okay, so they are Hofer-Lipschitz. So the difference of these spectral estimators for two Hamiltonians H and G is bounded above by the Hofer norm. Here, okay, I defined Hofer norm as integral of max minus mean, but so this Hofer norm is basically kind of equivalent to the Hofer norm that I defined. It's like I guess like this is bounded above, bounded below by half of that Hofer norm, and bounded above by twice of that. Okay, something like that. They have like Lagrangian control property. So if you have a Hamiltonian, time-dependent Hamiltonian, and on the Lagrangians, it is only a function of time, then you know exactly what they are. You can just calculate them. They're just integral of these functions of times. It's the average of these functions. They only depend, so the property 5 is that they only depend on the homotopy class of the path that H generates. And they have Calabi property. So if you have an open subset that is away from the Lagrangian link, away from all these circles, all of the Lagrangians, then the spectral estimator of that Hamiltonian is proportional to the Calabi invariant. And you have control additivity. So if you have some U, again, that is disjoint from the Lagrangian link, you have some H that is supported in U, and you have, and if you take any other G, then you have this additivity property. Okay. If there is no question about this, I will move on to the construction. Yes.
Can you remind us the Calabi invariant of H?
Oh, okay. The Calabi of H is just the integral of H over U with respect to omega to the n, something like that. Integral over U and integral over time of HT omega to the n. Sorry, I don't have something to write. I have to kind of say it on. I mean, I have my iPad, but it would take some time to connect it. I hope it was clear. Okay. Thanks for the question. So let's see how they are constructed. This part is going to be kind of very quick. I hope it's not too confusing. I'm going to remind like this bulk deformed Lagrangian for homology. Well, maybe I will kind of skip this part, and I will just say, well, let's talk about this. It's fun. So I have like a Lagrangian submanifold, which by definition is like omega restricted to the tangent bundle of L is 0, vanishes, and it has like half of the dimension of M. And I will take, you know, some almost complex structure, which is omega tame, and then the lambda is going to be the universal Novikov field. Nu will be the evaluation. Like it doesn't matter much to know the definitions of these things. But I just want to give a sense of what is the construction of these CKBs, because they kind of play the main role in this talk. It doesn't make sense to kind of talk about something without defining it. So, and then you take like on the cohomology of L with coefficients in the universal Novikov field. You can define this A infinity structure, which is roughly defined by counting holomorphic disks with boundary on L and with marked points. So, for example, the operation M3 takes, like, let's say it takes 3 homology classes, X1, X2, and X3, and it counts like sorry, by counting I meant, so you take the space of holomorphic disks with 3 mark points on the left that go through these cycles X1, X2, and X3, and then you look at what is the cycle that is traced out by the last marked point, and then you get something in here, like homology of L. And this is how like these operations are defined. Very roughly, it's quite technical to define these things. And then you kind of take this A infinity operation, then you deform it by some box, which is like a quantum homology class of M and this coefficients, right? Some homology class with coefficient in this positive Novikov field. And then you take like a B, which is like you can think about this as like a one form in L, and then the way you perturb your operation is just by adding some mark points, like interior mark points here, and some boundary mark points, and you can sum over all of these guys, and they have to be weighted. So the general idea is that you just add some mark points, and this is how you kind of perturb your infinity operation. And what is good about this perturbation of this infinity operation, infinity structure, is that if you take a B, like fix your bulk class in homology of M, and a B will be called a weak bounding cochain if it satisfies this equation, which sounds a bit, it seems a bit scary. It's called like Moore-Cartan equation for some C and the Novikov ring, lambda plus. Then what happens is that if B is a weak bounding cochain, then this M1 operation actually squares to 0. So let me just show you where was this from? Like, so M1 is going to be from H star to H star, right? So you can think of this H star as some complex, and M1 is going to be some differential. It squares to 0. Sorry for going back and forth. So it squares to 0, and then you can define this homology of this complex, and that's like this Lagrangian bulk deformed Lagrangian Floer cohomology. And here is the remark. So if your L is a tori, which is the case for us, is we have this Lagrangian link that is kind of consists of toris, right? It's like multiples, like products of circles with circles, right? And let's assume that all of the elements of each one are weak bounding cochains. So their corresponding M1 operation squares to 0. And if I take B as a critical point of this potential functional, which was defined here, so it takes any B to this constant C. If I take a critical point of the potential functional, then actually M1 is equal to 0. And then this guy is going to be just, kernel will be the whole space. It's going to be the cohomology of L. So immediately you get like Lagrangian for cohomology on the left is isomorphic to the cohomology of L. In particular, it will have a unit inside, which is the Poincare dual of the fundamental class of L. And moreover, this guy in the setting is actually isomorphic to homology of some four-type complex, which has some action filtration. And so this group is going to have some filtration on it. And then you can define a spectral invariant. So take any homology, like cohomology class of L. Think about it as an element here. And you map it by, so this was called phi h. So this isomorphism. So I did not, but like just to, I did not define this. So don't worry if you haven't missed, if you don't understand this word. So it will take a while to define this. So what is important is that this group has a filtration. So if I take a cohomology class and map it to the other group that has a filtration and represent it by different representations, right? These are the generators of the other group, and I take all the representative, and then I look at the biggest filtration that they have, right? And then I infimize over all the representatives. So if you have seen, spectral invariance before, this is easy to digest. If you haven't, it's probably a bit crazy definition, but it's hard to digest this for the first time seeing it. So, but now how are the spectral invariants? How are the spectral estimators defined? We go back to our favorite manifold in this talk. So productive spheres. And then what you take the kth fold product of this MA. So you multiply MA by itself k times, and then you divide it by this symmetric group that is acting like just it's the group of permutations of k elements. And then this quotient is not going to be a symplectic manifold, but it's going to be a orbifold, symplectic orbifold. It's going to have some singularities. And then what you do is you take this Lagrangian link that we had. So Li is like L1 is this lower circle times the equator. L2 is this one times the equator. L3 is the equator here times the equator, and so on. So you take this Lagrangian link Li, and then you multiply them like L1 times L2 until Lk. That's going to be a Lagrangian inside X, which is the product of this divided by Sk. But it's gonna be disjoint from this fat diagonal. It's going to be disjoint from that, and that is actually where the quotient of this diagonal is the singularity of your orbifold. So this L is going to fall into this regular part of the orbifold. Like it's going to be away from the singularities. And in such a situation, you can define again, for symplectic orbifolds, you can define Lagrangian. Like this, if you have a Lagrangian, nice Lagrangian inside like this regular part of your symplectic orbifold, you can you can define again this Borg deformed Floer cohomology. It's going to be, you know, in this setting that we have, it's going to be isomorphic to, again, Floer cohomology of L. And then the way we define the spectral estimator is that you take a function of your original manifold, like this product of a sphere, time-dependent function, and then you just define it to be the spectral invariant of H, where H is just the product of F with itself, K times. So H is defined on X, which is, you know, you take the product of MA, K times, and you take this as spectral invariant and you divide it by K. Now this part is not so important. Divided by K is just to kind of, you know, have a nice bound in this Hofer-Lipschitz property. Okay. Sorry, this part was very quick. I hope, but for the rest of the talk, which is like, I guess, 2 more pages, it's not so important to understand this part. But if you have any questions, please ask. Okay.
So, sorry, H appears only when you take the action, or?
Yeah, exactly. It's like, what do you mean if H appears?
I just want to see what's the so how does the H appear in this spectral invariant, just in the action, right? Like
Oh yeah, like in defining in like
C.
this object, yes, exactly. The only thing that you need is like the action filtration that H induces on this for complex, yes. That's the only place that it appears, yes, exactly. Which could, yeah. Yeah. So let's move on to the main result. So you take 2 of these spectral estimators, as I don't know if did I forgot to say, I guess, that these CKBs are not C0 continuous because they're kind of on some special Hamiltonians which are kind of away from the Lagrangian link. They're proportional to the Calabi invariant, and Calabi invariant is not C0 continuous. You can just, you know, take a very big bump, and then that's going to be, you know, C0, yeah, that's going to be like C0 small, but it's going to be, it's going to have like big Calabi invariant. Yeah, the integral will be very big. But if you take like a difference of 2 of these guys, then that's going to be C0 continuous. But only like we prove it only on disk times disk, because of the whole story that I've been saying was about, you know, extension and fragmentation lemma that are going to be used. They're both like on disk times disk. And if you remember, I said why we need disk times disk, but not a sphere times a sphere. It's being compactly supported in a disk, and being identity near the boundary was important. So it's a result of Gromov that the space of compactly supported Hamiltonian diffeomorphisms of disk times disk, or in general any starship domain in R4, is contractible. In particular, the pi1 of this group is trivial. And if I take my invariant tau and restrict it to, so if you remember, tau only depended on the homotopy class of the path that H generates, right? That the Hamiltonian generates. So it is defined on the universal cover of Ham. But if I restrict it to disk times disk, because pi1 of Ham is trivial, then it immediately descends to Ham. So it's going to be an invariant on this group And so the main theorem is the following. So this invariant tau defined in the group of Hamiltonian diffeomorphism of the polydisk is C0 continuous. So any question about this statement before we kind of see the very short proof? Okay. So the proof is easy, given the fragmentation and this Hofer approximation lemmas that we proved. So if you want to prove something is C0 continuous, okay, you fix an epsilon, and then you fix also your point in this space, and you want to find, you know, a small neighborhood of this theta such that any element in that neighborhood has value, like the tau value of it is close to tau of theta. Okay. So let's fix this element, and then let's fix a disk B disjoint from the Lagrangian link. So we have this picture again here. So this is like the biggest sphere times the smallest sphere, and our polydisk, this guy, is like, you can think about it as, you know, a disk embedded like on top of the first sphere and on top of the second sphere, and you just multiply them. And some of these circles are contained inside this disk, some of them not, it doesn't matter. But all you need is a B like this, a small disk that is disjoint from all these circles. So in particular, disjoint from the Lagrangian link. And you look at this U, that is like this small disk times the second disk on the right. So given theta in Ham of disk times disk, let epsilon be small. Let delta be small enough, depending on epsilon and b. So this delta is given by the theorem about this Hofer approximation. I want to go back to the theorem. I wish I had it here, but so let me not go back, but just like describe it here. So if you remember, like if you were C0 or small, so it was saying that for any epsilon there exists a delta such that if you're C0 close to identity, then you can approximate this Hamiltonian by another Hamiltonian that is supported in this U that we just defined, and it has Hofer distance smaller than epsilon from your Hamiltonian. So okay, let's take this delta, and then just define, you know, the C0 neighborhood of theta, nu of theta by, you know, just these elements. Like you take all the C0 small maps, C0 small Hamiltonians, and you multiply by theta, you get a neighborhood of theta. And then let psi be supported in U, and the Hofer distance from phi inverse or from phi to be smaller than epsilon. So the existence of this psi was proved before in that theorem that I just explained. So you actually have a psi that is kind of supported in this small disk times this right-hand side disk, and it is close to phi in the Hofer topology, in the Hofer distance. And now just we want this value to be smaller than epsilon, right? Just by you want to prove that it's continuous. So so we take this value like tau of theta minus tau of theta times phi, and we can we can kind of replace this guy by this guy because of this controlled additivity property that I mentioned. Remember that tau is the difference of two of these guys, and both of these guys are additive, right? And they kind of split. If I plug in theta and psi into here, both of them split. C of theta psi will be C of theta plus C of psi. Okay, they have different parameters. They're different functionals. But if you remember, both of them satisfy the Calabi property. So the value of each of these guys on psi is equal to the Calabi invariant of psi. So those two terms actually cancel. So I can just replace this with this, right? And now I use the Hofer-Lipschitz property. So this guy is bounded from above by this guy theta phi inverse. So that is equal to the Hofer norm of psi phi inverse, which is smaller than epsilon. So basically, given any epsilon, we found a delta such that basically we found the C0 neighborhood of theta such that if you're in this neighborhood, then the value of tau is epsilon far from the value of tau and theta. Okay. Okay, I'm presenting too many proofs. I hope it's not confusing. So, is there any question about the proof? Okay. So let's move on to one more application, which is this is the last. I'm already over time. Sorry about that, but this is the last slide. So what we prove here is that take the group of Hamiltonian diffeomorphisms with the Hofer distance, and then look at this infinite dimensional space, which is the space of smooth functions, compactly supported smooth functions on this interval, 0 and R. If these parameters actually satisfy some technical condition, then you can embed this space with equipped with the C0 distance. You can embed this space isometrically into the group of Hamiltonian diffeomorphisms. And the embedding is just by this picture. So you take one H and you kind of look at this function, this 1p function, which is a kind of an even function, and it's basically kind of in this part is kind of rotating. But by this picture, I just mean that it's just the rotation of the spheres in different directions with different speeds, like depending on the derivative of h. So yes, and you can just prove this embedding is an isometric embedding. So the Hofer norm of this flow that is kind of rotating the sphere in this weird way is exactly equal to the C0 norm of h. One direction is easy. It's just Hofer norm of the flow is bounded from above by the C0 norm because it was generated by h by the Hofer-Lipschitz property. Sorry, by just by definition. And then the other way is using these C0 continuity of these estimators that we just proved. Which is the proof is very technical, so I decided not to say it, and I'm already over time. So thank you very much. That's
Thank you.